Right. So next thing I'd like to do is I want to look at filling the inside of this structure a little bit, because right now we can see all inside there, which I like, but it's kind of empty. It has a few lines in it, but I think we can make that look really cool if we fill it with some like techie, greebly lines and things. So let's talk about how to do that. We're going to jump back to this point in our node graph, and we're gonna go back to the original cube because I want to fill this entire shape. Now we'll worry later about any intersections or anything that we have. I just want to start here and fill this shape up. So the first thing I'm going to do is I'm going to drop down a points from volume SOP. Now the points from volume SOP, that's it does just what it says it does. It creates points from a volume. So let's wire it up and see what it does. Cool. There's our grid of points that has filled that volume. Awesome. I'm just going to get rid of this color SOP. We don't really need that anymore. And what we're going to do is we're going to copy a bunch of boxes onto these points. We're going to do a copy to points. And we're going to do a box SOP like this. And we're going to copy the points, copy the box onto the points. All right. So they're a little big at the moment, and I could scale them manually, but then I'd have to do that every time I change the density of these points. What I want to do is on the points from volume SOP, I want to click on add scale attribute. And what that's going to do is it's going to add this little p-scale attribute, and it's going to scale those boxes down so that they fit a little nicer. Now, if I go in and I uniformly scale those boxes down to about 0.5, we should be in good shape. They should fit all nicely together there. Awesome. No gaps or anything like that. That's kind of just what we want, but it's filling that entire space with boxes. Okay. So now that we have this kind of box grid thing, right? What I want to do is actually fuse all those points together. So we're going to use, conveniently enough, a fuse SOP in order to do that. So we're going to actually fuse all these things together. So here we have 47,000 points. And on the other end of this, we have 10,000 points. So clearly that fuse SOP is doing something pretty significant. And actually, before the fuse SOP, what I want to do is I want to get rid of the polygons in these boxes and just leave the edges. And we can do that with something called the ends SOP. That's this guy here. We're going to drop this right in line. We're going to go to the end SOP, and we're going to go to this close U parameter, and we're going to change that to unroll with new points or shared points. Kind of doesn't really matter in this case. We're going to do unroll with new points. And what that does is it does exactly what I wanted it to do, which is to remove the polygons, but actually keep the edges. And now when we do the fuse SOP, now we're fusing together all those points. All right. So I kind of have this wireframe volume cube thing. And the reason I have this is because we're going to use we're going to use these boxes, all these lines, as the basis of our kind of circuitry grid thing that's going to happen inside of our cube. And we're going to do that using a SOP called find shortest path. And again, that kind of does exactly what it says it does. It finds the shortest path in a geometry from point A to point B. So we need to give this some starting points and some ending points. We need that first. And we're going to use a group expression SOP in order to do that. Because basically we need two groups. We need a start group, we need an end group. And we're going to go to the group expression SOP. We're going to change the group type to points. And we're going to call the first group start. And I'm just going to create a group of random points. I'm going to say this vex expression here is more or less a conditional statement, if you will. So I'll say let's say rand at ptnum is less than 0.1. So what that means, what that's telling it is generate a random number between 0 and 1 and use the point number as the random seed. So each point will get a totally different random number. And if that number is less than 0.1, put it into the start group, which it did. You can see all of these yellow points in here. So we have 1,080 points in there. So this group expression SOP, I can actually put multiple group expressions in here. So I'm going to hit this little plus. I'm going to add another group expression. And I'm going to call this group end. And I'm going to again say rand at ptnum, which means just generate a random number between 0 and 1 based on point number. And I'm going to say make if that is greater than 0.9, put into the end group. Cool. So again, we have about 1,000 points in that group as well. Great. So let's wire that into our find shortest path. And find shortest path is a little angry because it doesn't have any start or end points built, but we're going to drop those groups into here. We're going to say start with the start group and with the end group. And you can kind of see what that's doing, right? Like, that's sort of cool. It's not quite doing what I want it to do, but it's starting to get there. It basically is, it's treating that entire grid of cubes, this thing, as a single object, and it's finding the shortest path from the start group's points to the end group's points. And at the moment, it's doing from each start to any end. So it's going through every single start, all 1,080 start points, and it's just picking an end point for each of them to try and go to, and it traces a path through the geometry to get there. I'm going to change that to from any start to each end. See what we get. All right, it's not quite as interesting. Let's try each start to each end. That's going to give us a lot of geometry. And you have to be careful with this one because it will generate a ton of geo. Cool, so that's definitely way too much. Let's go back to any start to each end. And let's do this. Let's change the number of starting and ending points we have. Let's reduce, so this says from any start to each end. So we know that the ending points are always going to be considered. Let's reduce the number of starting points by reducing this number here. Let's say 025. So that way we get longer lines because we have fewer start points. Let's take that down to like 0.1. Now we have longer lines because we have fewer start points. Likewise, we could take the ending points down a little bit to include more ending points because it's going to go to each ending point. All right, that's pretty cool. That's starting to feel a little bit more dense. Now, I could also increase density by increasing the number of points in our volume. So right now, the point separation is determining how many points end up in here. And at the moment, it's 9,261. If I reduce this point separation to like 0.075, I will get more points because the points are less far apart, which means we need more points to fill the volume. Now I have 19,000, so I have considerably more. Let's see how that has affected. Yeah, there we go. We're getting really dense, but still like kind of grid-like structure that's pretty easy to see. That's pretty cool. It would be easier to see if perhaps there was like a gradient on each of these paths, right? Right now they're all white. It doesn't really do that much good. So I want to show you something that's kind of unique to Houdini. If I just drop down a line SOP, out here. Just a regular old line. I'm actually just going to offset it a little bit from the center so we get it off of this thing. The line SOP, by default, it only has 2 points. It doesn't really matter how many points this thing has. I'm going to keep it at 2 for the moment. What we can do is we can actually UV this line. And it sounds odd to the idea of UVing a line, because really all we're going to be considering is the U component. The V component is just going to be 0 no matter what. But we can actually UV this line. So we can say drop down a UV texture SOP, like that. And what we want to do is make sure that we change the attribute class to points so that the UVs end up on the points, because UVs are just another set of data as far as Houdini is concerned. It doesn't really care where it is or what you're doing with it. It's just more data. So we want to change the texture type from orthographic to rows and columns. And what that's going to do, you can see, this is the UV attribute that I'm interested in. It's the U component. And 0, the number is 0, and in 1, the number is 1. So if I drop down a color SOP, I can actually visualize that. I go ramp from attribute and say UV. You can see I've got this kind of like green color at the bottom, this kind of yellow color at the top. I don't really want yellow and green so much, so what I'm going to do is actually create a float attribute just based on that UVX attribute. I'm going to do that in an attribute wrangle. You could do it in a VOP too, but we're going to do it in a wrangle for right now. We're going to say, we're going to create a brand new attribute. We're going to call it f at gradient is equal to at uv.x. So it's creating a float attribute just off of the first parameter, the u parameter, on the UV. So we won't see any change here until I go in here and tell this to no longer be mapped to UV, map this to grad. Cool, there we go. So we have black at the bottom, white at the top. Now with this color SOP, of course, I can change that gradient. We're not going to see a great deal of change because we only have 2 points. But if we up the number of points, we could come back to our color SOP and really tweak this. This is much more interesting. So let's go ahead and take this chunk of information here. Let's get rid of this line SOP. We're going to take all of this, and we're going to throw it under here, and we're going to hook it up to our find shortest path. That's a little bit more interesting to look at. So now it looks like each of those has this sort of hot tip, and it gives it a little bit more of a sense of movement and direction, which is pretty cool. And likewise, I can drag in a little bit more dark area. We can really just kind of isolate those light areas like that. That's pretty cool. Now let's go ahead and merge that into the rest of our cube setup, because I just want to make sure that that's going to work with everything else that we've got going on. We'll plug that in. We'll check our merge. Now we do have these little points kind of sticking out on the edges, and I see some kind of creeping through. And the reason for that is this points from volume generates points pretty much like right to the edge of my box. And I kind of want to remove that first row all the way around, just so we don't get any of those kind of extra lines sticking out. For that, I'm going to use a peak SOP. And the peak SOP, that takes the input geometry and essentially shrinks it in on itself or expands it on itself. In this case, it's basically going to act like it's scaling, which is, you know, in and of itself not terribly interesting. But the peak SOP is incredibly handy for many, many things. So we'll come back to that. All right, so that should eliminate a kind of first row or so, which should make it fit nicely inside our box. Yep, there we go. Cool. So we have all of those kind of techie lines in there, filling our box. We'll see more. We'll end up deleting out some of these polys, so you get some bigger holes so you can see inside a little bit clearer. But they fit nicely. They're no longer like coming outside the box at all or running along the surface. They sit nicely inside.